All right, section 4.3, Riemann sums and definite integrals. We're going to use some of the information that you guys looked at in section 4.2, and we're going to combine that with some of the notation we saw in 4.1. Okay, so this is a combination kind of section. There is a lot of writing on this front page, so if you do not have this printed out, you're going to regret it today. Is that you, Rachel? Oh, okay. Does anybody not have this printed out? Okay, so for those of you who just raised your hand, just write down the blanks and print this out later and fill it in, because you're definitely not going to have time for that, okay?
You'll post the video, right?
Yep, I will post the video. All right, Riemann sums.
Oh, wow.
So we're going to let f be defined on a closed interval AB, and we're going to let delta be a partition of that interval given by a is equal to x0 is less than x1 is less than x2 up to xn is equal to b. I'll draw you a picture. This really is not as complicated as it's worded. Where delta xi is the width of the ith subinterval from x sub I minus 1 to x sub I. If c sub I is any point on the ith subinterval, then the sum from I equal 1 to n of f of c sub I delta x sub I gives us that value gives us the sum. This is called a Riemann sum for the partition f of f for the partition delta. And the sums in section 4.2 that you did are actually examples of Riemann sums, but there are more general Riemann sums than those are covered here as well. So let me just look at the interval with you of what this references so that you can feel like you've got a handle on it a little bit better. Our interval goes from A to B, okay? And they're telling you that A is the same as x sub 0 and B is the same as x sub n. And they're just subscripting them that way because that way we can have however many we need. So if you have 10 locations between, this would be from x0 to x9. Okay? That kind of stuff. So you're just being able to do it generally. And somewhere in between here, these are all partitions, and they're x with subscripts. This is x1 and x2 and x3 and x4. Okay, so these are all of our subscripts of different locations between. The subintervals don't necessarily have to be the same width. They could be different widths. We treat them like we kind of have to have them the same width because since it doesn't matter, it's more convenient to treat them as though they're the same. It's easier to work with mathematically because in the end it doesn't end up making any difference whether they were different or the same. C sub I is any point in the ith subinterval. So if you were looking at a point here, it doesn't have to be halfway, but there is a C sub I in between here. So if this would be the second subinterval, so this would be C sub 2. So this is subinterval number 1, this is subinterval number 2, so there is a point in between x2 and x1 that's called C sub 2. Okay, and we can do that with any point in between them. Then if we're finding that f of c sub I, well, c sub I is the x value. So what happens when you take the x value and put it into the function? What do you get? You get the y value. Okay, so this is actually giving you the height. So this right here is the height. It's the y value's height. And delta x sub I is the width of the interval. Does that sound familiar?
Yes.
So we did in 4.2. So this is like saying height times width or length times width, if you prefer. It's area. Okay, so this is simply a notation for the area where it's done more generally than what we did in 4.2. So you saw that in 4.2, but you saw it for very specific cases. Okay, this is all this is talking about. Sort of a more formalized and more broad description than we did in 4.2. A definite integral then, if f is defined on the closed interval AB, and the limit of the Riemann sums over the partitions delta, this is right here, the notation, exists as described above, then f is said to be integrable on AB. The limit is denoted as the limit of the absolute value of delta approaches 0 of the summation from I equal 1 to n of f of c sub I, delta x sub I, equals the integral from a to b of f of x dx. Now that looks somewhat familiar. That looks like section 1, right? What's different about how that looks though?
Yes, endpoints.
Yeah, it has an a and a b. There's endpoints on it. We didn't have that in section 1, correct? So we'll connect those pieces together later, but that notation, except for those the A and the B, should look familiar. Note this right here, this piece, and this interval, or this limit notation. That's telling you that the widths of those rectangles that we just decided on are going to go to 0.
What is the, like, is that double absolute value?
It means magnitude. If you haven't gotten to it in physics, for those of you who will be taking physics, at some point you'll see it there as well. It means magnitude, just the length. What's that? One line's absolute value, which is distance, but magnitude is also another form for distance. They mean the same thing for what we're doing. Yeah. Okay, so all this is really talking about is these widths that I had in my picture over here are going to 0. So if the widths are going to 0, obviously that also means that the rectangles are becoming more, right? Because you're still covering the interval from A to B. So by the widths becoming next to nothing, practically nothing, you get infinitely many rectangles, and that's why it doesn't matter if the widths are all the same or not, because they're all going to 0 anyway. So we might as well let them all be the same, because it's easier to work with.
So could that be notated as well as n not going to infinity?
If you represented it by the subscript for the number of intervals, yes.
Okay.
They're referencing it by the delta in this definition. Yeah. The limit actually has a name. It's called the definite integral of f from a to b. So this notation, definite integral, is important. The number a is called the lower limit, and the number b is called the upper limit of integration. And we will use those three phrases over and over and over again. So those are important phrases to remember. So when you hear definite integral, you should know it's talking about this thing in the box. When you hear lower limit, it's the lower value on the definite integral, and you hear upper limit, it's the upper value on the integral. All right, now we've had some continuity sort of things happen in the past with derivatives, right? We said if it was continuous and smooth, we could find the derivative. That was one of our features about derivatives. Well, if something's continuous, it's also integrable, and you don't even need the smooth part. It doesn't have to be smooth. It could have those cusps. So the interval could look like that. It's continuous, but it's got this weird point where it's not differentiable. That's okay, though. We can still integrate this. Okay? Because what it is when we're finding an integral is we're finding the area below this. And while it may be awkward and we may have to sort of divide it up so that we can only consider one piece at a time, I drew a tent. We could find this area and we could find this area and we could add them together, right? So that point where it's got this sort of funny shape to it, we could kind of break it apart so that we don't have to deal with the funny shape. Right? We are finding area under curves. So it's integrable on AB. That means that if it's continuous, then this definite integral exists. Okay, we can find it. I don't think that I put any of this on there as a memorize this to rewrite it down later.
Just the Reimann Sum definition.
Riemann sum, what?
Just that one.
The one from before over here?
Yeah, memorize
This one? You want to memorize this one for me? More power to you, Garrett. All right. The last one on this front page. The definite integral as the area of a region. If f is continuous and non-negative, okay, so that's an important feature on this one, on the closed interval AB, then the area of the region bounded by the graph of f and the x-axis and the vertical lines A and B is in fact the area. So let me show you what this is talking about and then show you what it means doesn't happen kind of by default. So you have this curve, and this is my x-axis, and here's my y-axis, and you've got these values a and b, right? And this is saying that if I find the definite integral here, what I have really found is area. And that's kind of how I've already talked about it, right?
Yeah.
But the only way I drew it, and the way that this is saying that this description fits for, is if it is a non-negative graph. Are you guys with me?
So far, we've only learned how to do an estimate.
It's true. We're going to learn how to do the real one here in a second. But what this is saying you can't do this for, or can't describe this as, is let's say that the graph does this. And A is here and B is over here. Well, if this happens, then we don't actually end up finding the area when we find these pieces. And we'll talk about it a little bit more later, but my pet name for it is called net area. If I find this definite integral, what it will actually do is it will find this area and it will pretend like it's a positive number, and it will find this area and it will pretend like it's a negative number, and it will add a positive and a negative, and you might get 0 because this graph looks pretty balanced.
Can you just break apart that into 2 parts?
Yes.
And then add them
You
up?
flip it
Yes, you
up.
can, and we will. You could think about it as flipping it up, or you can think about it as taking absolute value, and we will do it from that perspective. All right, we have time for one example because it's really fast, and then we'll pause. This says to set up the definite integral that yields the area of the region, do not evaluate. And this is on page 273. It actually has a graph for you. I'll draw the graph in here in a minute. But the function is actually f of x equals x squared. And the graph that it draws in on that particular page looks like this. Yeah, the graph shows it. It has a 2 here. And it draws this down here. We'll use gray because it's fun. Like that. And then it shades it in. Oops.
So is it from 0 to 2?
Yeah.
Yes, it shades it in. Like what the graph actually shows you when you look at that particular problem, and some of your own website are going to do like this. And so this is where the problem starts. It's the part that I didn't have already written down, but that's the part that if you go to page 273, number 16, you'll see. Okay, so they'll look like this. What it's wanting you to do is it's just wanting you to set up the notation so that you get comfortable with notation.
Integral 0.
So the integral notation, and then what did you want to do next?
0 on the bottom.
Okay,
2 on the top.
okay,
Put the f of x, which is
X squared.
x squared.
Is it saying from 0 to 2?
Yes,
Keep it
and
here.
that's got because it's a 0 over here.
Why is the 0 on the bottom?
It's not on the bottom, it's representing this location right
Your
here.
lower number has to be at the bottom of your
Oh,
integral.
yes, you're going, it's not really, it doesn't have to be, but we're chewing this interval from the left to the right.
Good choice.
So we'll talk about what happens if somebody puts it in backwards later.
Okay.
But as we're setting it up, the whole goal is to go from left to right, so smaller to larger. So smaller value goes on bottom, like Fallon mentioned, and then the larger value goes on top.
Okay.
X squared is our function, and then there's something still missing.
Dx.
Dx. Anytime you have this notation, you're going to have this notation. They go together. They're sort of like a front end and a back end of a parenthesis. Okay, you can't start one and then just leave it hanging.
Okay.
All right? What it really means at the end is it's telling you with respect to x, that is, this thing I've written down has a variable x in it. And again, the reason that comes into play later, more important than now, is because the integrals we work with in further advanced courses of calculus do have more than one variable. Okay? All right, we will stop there for today.